instead of, I'd rather do like the Sesame Street song, okay, which one of these is not like the other? So how is A not like the other? It's the only one. 5 what? Why is that different from all the others? Well, they have 2's. They all have a 5 and 6 2's. How is A different like all the other ones? What kind of arithmetic? Come on, we'll get there.
Is it because it's an arithmetic sequence?
It is an arithmetic sequence. You're getting a little too complicated. It's the only one that just has addition. There we go. Okay. So only addition. So I'm going to make a little text box. Only addition. Now, if you look carefully, first and the second one are the same. It's the same sequence. You'll get the same sum. It's just B has multiplication. Okay. Same thing, but with multiplication. Okay. Now, like I said, they all have a 5 and 6 2's, but C is not like any of the other prior ones. How is C different? It's got an exponent. But basically, A and B are the same, and C and D are the same. Exponent. And this one doesn't have any exponents. Exponent, well, same as C. Same as C. No exponent. Okay. So when you see these, which one doesn't belong, it's really, how is it different from the others? Okay, we are going to revisit our paper slicing. So if you remember, we created a recursive formula, which I will put up here. It's also up on the board, but for those people playing at home, they can't see. So C of 1, not CX. So C of 1 was 80. And then C of n, in general, we are taking each paper, cutting it in half. So 1/2 of C of n. We can't start using this sequence until our second term. Whoopsies. Okay. Anybody remember how to get the equal to sign? Just press. Nope, equal to. And I'll put greater equal to. Right. So, instead of writing the recursive definition, which is up here, wrote it as an explicit. So I'm going to just put this. So we call this the explicit. Okay. I need a P explicit rule or definition. So this publisher likes to use the word definition. Any other publisher I've seen use the word rule. Okay. So what I want you to do is explain where the different terms in the new explicit definition came from. I'll give you a hint. Look at the recursive rule. So just take a minute, see if you can pull those pieces together. How about it, Diana? What does the 80 represent? Yeah. Not the width, not the length, but when we put it together, what do we get? Length times width, Diana, is? Area. Okay, so area. So the area of the original piece. Hello. Trying to get him up to speed. Was 80 inches. Okay? And 1/2, 80 square inches. Thank you. So I'll use all my words. square inches and the 1/2. What's 1/2, Sydney? Okay, 1/2 represents cutting the area in half. That's all. Doesn't have to be any trickier than that. Okay? Only thing slightly mathematical about that sentence is the numbers and the units of measure. Okay? All right. Find the area after 10 cuts when we use Claire's explicit formula. It's going to be teeny tiny. I don't want you to round, and I want you to use proper units of measure. A sentence that represents the approximate area. It's going to be small. So, I don't know. So go to Desmos. As teeny tiny. Hey, we can copy from Cami into Desmos. Do you think it works both ways? Yeah, it does. So if I just take that number and just click on it, not with my finger, obviously, it doesn't like it. Okay, there we go. Double click on it, Control C, come back here. Now, when you're asked a question in English, I want you to answer the question in English. So you say, the area of the paper after 10 cuts. You can use the words in the question. Look at that. Paper after 10 cuts will be space Control V and then square inches. I'm going to use the inches squared, and there is a superscript notation, so you don't have to hit Shift 6. But watch this. Right up here, if I do superscript, there's square inches, right like that. And then I have to press it again to turn it off, and it'll come back down. Okay. Do you think this is physically possible? Okay. Something that's got 78,125 millionths of an inch. That's physically going to be possible to do. Okay. All right. Changing the scenario. We have Kieran. Instead of cutting in half, read what it says, and then we'll see if you can fill in the table. So, since we're cutting off a 1-inch width strip, see now if you can fill this in, and if you filled this in already, great. For part B, explain what each number means in English, and then for part C, you're going to write the explicit rule that follows along with what's going on, and then lastly, you're going to compare this to what we did before and figure out which number's bigger. I would suggest at the very least is I would write this part, and I don't know, maybe you don't need to show repeated addition. Instead, you do 80 minus 3 times 8. Okay? And it's really not that extra work because you know how you can copy and paste with everything else? Well, you can do that here. Control A, Control C, come down here. Now instead of 3 cuts, we're doing 4. Paste, come back, change this to 4. Okay? Control V, change 4 into 5, and then just do the arithmetic. Well, 80 minus 40 is 40. Up here, that's 40, right? 80 minus 32 is 48. We got a 72 and a 56. Okay, so that should be the easy part. One sentence with the numbers 80, 8, and 6 explaining what each number represents. We've already talked about the 80. The 8 and the 6 is going to take a little bit more work. 30 more seconds. So start with capital K, N, close, equals. We started off with 80. It's really the same as 80 minus 8 times 6, but instead of 8 times 6, it's 80 minus 8 times n, that's it. Where n is the number of cuts. What's bigger, K6, K of 6, or K of C of 6? So we already got C of 6. We're real close. We have C of 5 is 40. Take off another 6 inches. So K of 6 is equal to 80 minus 8 times 6, which is 32. That's something we could see physically. Oops. Yeah. And then C of 6, you can either use the recursive definition, but if you use the recursive definition, you just have to keep taking half. Or you can plug it into the formula, which we did already with Desmos. Just change your 10 into a 6. And it's relatively small. Okay. Still big enough to see. Not sure if we could physically cut this. Okay. This might be like one of the last cuts we could physically do. So 1.25 inches. What's bigger? This is not a trick question. Okay. So Kieran's possessive apostrophe. Kieran's function value is larger at 6. Larger. Okay. And it doesn't have to be exactly like that. Which makes sense. If I keep taking half of something, it's changing each time. It's making it smaller and smaller and smaller by half, which is much larger cuts. Whereas here, I'm cutting off the same amount each time. So one of them would be arithmetic, and the other one would be geometric. So the geometrics can get smaller faster. All right. Sierpinski's triangle. I want you to represent this recursively. How many black triangles? So when in doubt, read. So not total, just the black ones. Okay. So take a moment, see if you can come up with a recursive function. So here we go. This is not a trick question. Ready? Danica. How many black triangles, Danica? Okay. So we have capital S of 1 equals 1 because there's one black triangle in our first step. Everybody can agree on that. Okay. Next part. It's not how many triangles total. It's just the number of black ones. So, parentheses, capital S of n equals. How many more do we have? 2 times as much? 4 times as much? 3 times, because we're only counting the black ones. So 3 times S of n, just like that, right?
No, minus 1.
No,
Why not?
it's the
Previous term. So in what we define the phrase English previous term in mathematics, what is it, Anjali?
n minus 1.
N minus 1. Okay. Close, comma, n greater than equal to 2. Okay. So that is the recursive. Now what they did is they took the next step. All right. I've been teaching math a long time. Every once in a while I see something that kind of bugs me. And this kind of bugs me. It's not wrong, but it kind of bugs me. So we got Andre and Lynn are asked to write an equation. We're asked that it's not recursive. Andre writes this equation, S of n equals 3 to the n for n is greater or equal to 0. And this one, n is greater or equal to 1. Okay. I'm just going to preempt this. Both of these are mathematically correct. Which one do you think is more commonly accepted? First one or the second one? Starting at 1 or starting at 0?
Second one.
Yeah, it's mostly this one. Okay, so it's rare that you're going to see the 0, and here's why. Okay? Now, briefly we talked about this Friday. We said something was the 0th term, but it doesn't sound right. Okay, so unless you see a table of numbers where 0 is represented as n, take a look at the prior one. That's the case, because before we started cutting, the paper was whole. So when we had 0 cuts, it was 80. But But once we started cutting, well, we had a different formula than last time. But even further, I can put a 0 in here. 8 times 0 is 0. I'm back to my original piece, which makes sense. It's not going to happen that often. So more often than not, you're looking at the second one, even though they're both mathematically correct. Okay? All right. Oopsies. What are we doing time-wise? Oh. Okay, last little thing. This one's hard. Nobody in the other class got this. I'll be very impressed. I'll even give you a little hint. If we have a little less time. We're doing time-wise. Each of the missing pieces should have 2 parts to it. I'm sorry, what's 4 times 1.5?
4 times.
It's close though, right?
Yeah.
It's close. So we know the answer, but 4 times 1.5 is a little bit bigger than 6?
No, it's 6.
Oh. Oh, okay. Let's try it again. So what's 6 times 1.5?
9.
And 9 times 1.5?
13.
Oops.
Oh,
so close.
Bro.
Okay. So let's talk about how to do this. Give you an easier set of numbers. What's my common ratio?
2.
Okay. So each time I'm multiplying by 2. So to get my 1 over here, I multiply by 2 twice. So if I'm going from 4 to 16, I multiply by 2 twice again. So I have to multiply some number r twice to get the common ratio of 6 divided by 3. What's that common ratio going to be? I got to take what in order to solve the quadratic? Got to take the square root, right? So my common ratio is square root of 2. Remember I said that had to be 2 parts? So I take 3 and multiply by square root of 2. And then 3 square root of 2 times square root of 2 is 6. Because square root of 2 times square root of 2 is 2, and 3 times 2 is 6. So I multiply 6 times square root of 2. So this one's going to be 6 square root of 2. And I'm going to take a gander on what that last one's going to be. Take a guess. Come on.
12.
Danica? Nikki? No? Somebody said it. 12 square root of 2. Okay? Because each time I'm multiplying by square root of 2. So every other time, what happens to my square root of 2? Square root of 2 times square root of 2 is 2. So every other time. So my next one's going to be 24 square root of 2. My next one's just going to be 24. Basically, 24 times 2 is 48, etc. And then 48 square root of 2. So your common ratio does not necessarily have to be square root. Okay. All right. I'm going to leave the rest for you. Okay. Just one thing I want to talk about in this lesson summary. I kind of talked about this already. The more accepted way is this one up here. Okay. This one is not wrong down here, but I'm going to tell you this. I have not seen that used that often. And especially when the table, look at the table. What's the table not start with? It doesn't start with 0. Why would I mention 0 if it's not in the table to begin with? So I think this is not so good for this. It's not wrong, but this is a better representation. And then normally what we do last is we take things, that 4 doesn't want to be in front of there. What's the 4 want to do? It wants to be distributed. And if I distribute the 4, then I can simplify. So my final answer here will be 4n minus 2. So we are going to stop there. If you want to take a look at the cool down, you may. I'll put the answer up tomorrow. Working on practice problems.